today we have a guest from the University of Pennsylvania who will present his work on offline reinforcement learning. And our guest is Jason Ma. Jason Ma is a third-year PhD student at the University of Pennsylvania. He's advised by Osbert Bastani and Dinesh Jayaraman. I hope I do justice to the names. He is also a student researcher at Meta AI. His research interest spans the intersection of reinforcement learning and robot learning, and in particular, developing safe, specifiable, and scalable robot reinforcement learning algorithm. Prior to Penn, Jason completed his bachelor's degree at Harvard University, where he received the highest honor distinction in computer science and was a winner of the Thomas Temple Hoops Prize for outstanding undergraduate thesis. All right, well, we're very happy to have you today, Jason, and very excited about your work. So take it away. Thank you very much.
Great. Yeah, thank you for the very kind introduction, Samuel. So I'm going to present our paper titled How Far I Will Go, Offline Goal Condition RL via Advantage Regression. This is joint work with an undergrad at UPenn, Jason, and my advisors, Dinesh and Osbert. And also feel free to interrupt me in the middle if you have any question. Happy to answer them during the talk. Yeah, so let's just jump right into it. So what is the motivation for offline RL, offline goal condition RL? And I think it's like a vision towards a generalist home robot that can be in your room and help you do a lot of different things. And how might we achieve this vision? And I think this kind of robot needs to be able to solve many tasks and many different configurations of the same tasks. So you can think of there's a single task you want to solve, and there are many different configurations. And these configurations can be broadly categorized as distinct goals. For example, you want to push a mug on a table, so you might want to push the mug to different locations on the table. And if you just want to do learning in this kind of environment, doing online reinforcement learning might be too expensive, but there might be a lot of large-scale diverse data sets available, collected in many different homes. So the way to achieve a generalist home robot that can help you do a lot of things is one that has to be able to learn from offline data. And of course, offline reinforcement learning has been a very popular and growing field over the past few years. And the key distinction with online reinforcement learning is that we just use a fixed data set that's given to you to learn policy without any online interaction, which is first of all slow in the real world, and the second of all might not be safe because exploration necessarily causes changes in the environment and might damage your surrounding or the robot. And offline goal condition reinforcement learning is a particular type of offline RL in which the task is specified via reaching a particular goal configuration of the environment. So here you see a very impressive example coming from Google, where the goal is just an image of the tray that's provided, and you want the robot to be able to manipulate the tray such that the end configuration matches the goal image that's provided. And so I think offline goal condition RL is a very foundational thing if you want to reach a generalist home robot, because it's learning from offline data and it is trying to reach many distinct goals in the environment. So let's look at what prior offline goal condition reinforcement learning methods do. They typically adapt from online goal condition reinforcement learning methods. And as a result, they inherit many artifacts and heuristics from online goal condition RL. For example, there's this very famous mechanism called hindsight experience replay, where you relabel all your data with goal that you actually reached to provide more dense reward signal for policy learning. And also most goal condition RL methods use actor-critic architecture. But it's not clear that in the offline setting, these components are also necessary, and whether or not they actually improve or actually inhibit performance. And I guess one more thing that's not satisfying about the current state of art is that there's really a lack of theoretical understanding about under what condition, what kind of data set can these offline goal condition RL methods work. Offline reinforcement learning is sort of a mix of practical and a theoretical field, but so far goal condition RL has been quite empirical. We don't have understanding of what kind of data set, what kind of coverage the offline data set needs to satisfy in order to learn any kind of policy, let alone the optimal policy. So the central question that I want to answer or present to you today is whether or not we can learn and design a offline goal condition reinforcement learning algorithm that's developed from first principles, doesn't necessarily borrow existing components from an online goal condition reinforcement learning algorithm. And I believe by doing so, we might actually get a better algorithm that has theoretical guarantee and it can actually perform better because we have a very precise understanding of when this kind of algorithm might work. And so the particular method I'll present to you today is called goal condition F advantage regression. And it is derived from the first principles of state occupancy matching, which we will explain very shortly. But at a high level, it first enjoys what I call uninterleaved optimization. So instead of something like actor-critic, where you update the critic network and the actor network, in an alternating fashion, here you just update the value network in one go, and then fix the value network to update the policy network. And doing so has a lot of advantages. First of all, it actually removes hindsight experience replay. Like this algorithm doesn't need to do it at all, which is really nice in the offline setting because hindsight goal relabeling actually requires a very sensitive hyperparameter in the offline setting, which you can't really tune in the offline setting. So by removing it, it's actually more stable and much easier to use in practice. And also as a consequence, it has very strong performance guarantee. And finally, we show how this single algorithm GoFAR not only can be used to learn a policy, but it can also be used to learn an optimal goal condition planner, which is very interesting. And here are some of the empirical, environments that we tested on, including simulation environments, and also including a real dexterous manipulation environment where we have to turn the valve to any configurations on this platform. Okay, so before we dive into the algorithm, I just want to present some very short formalism of offline goal condition reinforcement learning. So as in reinforcement learning, we have a Markov decision process. The only difference is that in addition to the state space, you have a goal space. And in a lot of cases, the goal space could be identical to your state space if you have access to the low dimensional true state. And in addition to the initial state distribution, you also have a TG, which is the goal distribution that you want to reach at the evaluation time. So the reinforcement learning objective in this setting is pretty much identical to the standard one, except now you also sample a desired goal you want to reach in each rollout, and the reward not only depends on the state, but also depends on the goal. And in the offline setting, we assume an access to an offline data set denoted DO, and it has state, action, reward, next state, and additionally a goal. So the way to think about where this goal comes from is if your offline data set is collected by a goal-directed agent, then obviously each transition has an associated goal that the policy is trying to reach. But in the case that the data set is just random, then obviously there's not a goal that the policy or the collector is trying to reach. In that case, you can just randomly sample a goal from your goal distribution of the task and just label every transition with a random goal. And then the offline goal condition RL problem is just outputting a policy pi from your learning algorithm A that just ingests the offline data set. So as you see, we don't have access to MVP actually. And this policy is goal conditioned, is conditioned at state and goal. Yeah, feel free to interrupt me if there's anything that's not clear. And given this formalism, we want to learn policy pi. Okay, so this is all standard. And just before we jump into the method, another thing I want to give a quick introduction to is this notion of state occupancy distribution. So the way to think about this is that for every policy, when you roll out the policy in your environment, it generates a distribution of state and action it will visit over the course of its entire rollout. And this is the mathematical way to write this down, which is not super important to parse technically, but given the policy's state and action occupancy distribution, if you just marginalize over its action, you get a visitation distribution of states that the policy will visit. And since we're in the goal conditional setting, we just condition on a goal everywhere. And there's a one-to-one correspondence between a policy and the policy's occupancy distribution. You just take the state and actions distribution and divide by the state occupancy distribution to marginalize it out and get back the policy. And every state occupancy distribution must satisfy this, Bellman flow constraint, meaning that, every distribution D that satisfies this equation will correspond to the state occupancy distribution for some policy. And on the left-hand side is just the state occupancy distribution. On the right-hand side is, how likely you'll visit the particular state from the initial state distribution. And then if you don't visit the state in the first step, then it's, the chance or distribution of visiting some other states and action that lead into this particular state. And this is like a constraint that must be satisfied in order for this to be valid. Yeah, Sam, you have a question? Samuel.
Yeah, oh, you can call me Sam as well. It's just as good. I just was wondering about this mapping from state to goal that you assume. So it's defined by the state occupancy measure, right? So like, how do you know basically that like there is this state corresponds to a certain goal? And if you assume like a probability of 1 all the time in not for the state occupancy measure you compute, but the one you assume is provided by the dataset. So it's like binary, or is it a probability associated to being specifying the goal if you are in a specific state?
Yeah, so yeah, it is a probability distribution specified on a state condition on a goal. So you can think of the goal as literally just like extra dimension in the state space, right? Like there is nothing that's like super, special about a goal. You can concatenate these two just to get a state occupancy. But since we're in a goal condition setting, it's helpful to, separate state from a goal. But for all sake and purpose, you can think of them as like, different components of a giant state vector. I don't know if this answers your question, but maybe this will be clear as we continue.
No, I think it does. The only question I had is like, is it like deterministic in the experiments you've done? Is it always deterministic that for a specific state you'd be in a goal, or do you have like a stochastic approach to that? Like you can be in a state and then you may or may not satisfy the goal according to probability.
Yeah, I understand. Yeah, so that's something you get to define, right? That's kind of getting at like what the reward function is, right? Whether or not a particular state satisfy a goal. So that's actually like defined by the problem. Like you're giving offline data set that tells you whether or not a state satisfies a particular goal via the reward function. But that's something that the user gets to define, right? Like you can say, oh, the only state that satisfies a goal is just the goal itself. If states and goal states are the same, or you can define states that satisfy a goal to be like an epsilon ball around the goal, right? That's something you have control over. Yeah.
I see. Yeah. Thanks a lot for that.
Yeah. So let me just continue. So why am I introducing state occupancy distribution? The fundamental reason is this one-to-one correspondence between policy and the occupancy distribution, right? Like typically in RL, we think of an optimization problem over the policy, but a lot of the times if you translate the same problem into optimization problem over the state occupancy distribution, it gives you a mathematical formulation of the problem that's much nicer to work with and makes a lot of connections and the tricks a lot obvious to work with. And that's something we'll also explore in this work, which is why I introduced this kind of correspondence between a policy and the distribution of states it induces in the environment. Okay, so now after I introduce state occupancy distribution, here let's get into the technical part of this method. Basically, GoFAR introduces a state occupancy matching perspective of goal condition RL. So we think of reaching a goal as matching the expert distribution of an agent that can just teleport to the goal. So what do I mean by that? So in particular, we want to start out with a KL divergence minimization between your policy's state occupancy distribution and this distribution P of S given G, which essentially captures the distribution of states that satisfy a particular goal. So that goes back to Samuel's question to like, what are states that satisfy a goal? So this is something that the problem provides or you give it to the problem because the user gets to define the reward function. And we'll see how this ties into the notion of reward in the original introduction of the problem setting. And the way to think about this is just that you want to make the distribution of states you visit as close to the distribution of states that satisfy the goal. And the intuition is that obviously your policy pi must abide the environmental dynamics, right? Because it can't just like transport or teleport to a state. But P of S given G can be thought of as the state distribution of an expert that can just teleport to the goal in one step, right? So basically, like it doesn't even need to like take a step in the initial state distribution. It can just directly teleport to all these states that satisfy a particular goal. And the goal of your learning algorithm is to be able to make your agent run as fast as possible so you can like reach the goal as fast as possible. And in that sense, you would be able to minimize the KL divergence between the distribution of states your policy visits and the distribution of this like omnipotent teleporting expert. So this intuition sounds very interesting, and it's actually developed in a prior work of mine if you're interested to check it out. But does this intuition stand up to like math? Like whether or not this is like an actually rigorous thing is still an open question if you only look at this slide. So in the next slide, we actually show that this kind of state occupancy matching solves the general goal condition reinforcement learning problem that we laid out in the first introduction slide. So without going into the math too much, let's just parse this proposition. Basically, it says that for any reward function you give to the goal condition RL problem, right? For each goal in the support of your desired goal distribution, if you just define, this expert distribution to be this, which is this exponential reward over the normalizing constant, then the following equality holds, where if you maximize the negative state occupancy matching distribution matching problem, then it's equivalent to actually just maximizing the original reinforcement learning problem plus a state entropy maximization constraint. So basically what this says is that for any goal condition RL problem that you care about, that you want to solve with any reward, you can equivalently just solve a state occupancy matching problem where you define the expert distribution to be like this. And then you would actually be able to solve J pi by just maximizing negative DKL or minimizing DKL. And this says the intuition that we laid out in the previous slide is actually a valid approach to solve the general goal condition RL problem with any choice of reward in generality. Yeah, so if you read the paper previously, this wasn't in the main text, but this will be updated in like a upcoming draft. But this connection is important because it says whatever we are doing is actually a valid approach to goal condition RL. And it's not just a fancy, interesting intuition that may not make sense mathematically. So this proposition is nice, but it still doesn't tell you how to actually optimize the KL divergence at all, right? And in practice, in an offline setting, it's actually very difficult to optimize the KL divergence. Because if you write out the KL divergence, it will depend on your policy's state occupancy distribution. And so if you want to estimate this expectation in practice, you kind of have to write out the policy to estimate this term, right? But in the offline setting, you obviously can't do that. So it seems that we are hitting a roadblock. But the idea that this paper will use is using tools from convex optimization to get around the problems that's kind of intractable to a form or to an objective that only depends on your offline data set. And we're now going into how to do that. And this idea of using convex optimization to do RL has been explored in several prior work if you're interested in checking them out. And so the first step we have to do to get around this like pesky KL divergence is to derive a lower bound to this objective that's amenable to using tools in convex optimization. And in the paper, we'll show how to get this lower bound, but roughly you can think of the lower bound as consisting of two terms. So the first term is the expectation with respect to still your policy's occupancy distribution with the reward. And the second term is F divergence regularization. So in this paper, you can just think of F divergence as KL divergence or something. And the math here is not super important. And overall, this objective is just a reward, a policy optimization term with reward here, with the regularization. You see this kind of thing a lot in offline RL. So one thing I forgot to mention is that for your policy objective JPI, an equivalent way to write this out is just the inner product between your state occupancy distribution with the reward. If you think of the reward as a reward vector, so those are equivalent. So this is just your standard RL objective with that regularization. And so this has a problem, like how do you compute this reward? So because this reward is just ratio of two distribution, you can compute it or estimate it by training a classifier like in GAN. And once you train this classifier, the negative log of 1 over this optimal classifier minus 1 will actually just give you the reward. So if you want to see where this comes from, I would refer you to the original GAN paper, which does a nice derivation of this. But now we are just going to take this reward as it is. We assume, okay, we're going to train this classifier, which only depends on your offline data and your P of S given G, which you can estimate or actually have access to because you know what the reward is for all the offline data set. And using this previous relationship, you can back out P of S given G using R. Okay, so that gives you the classifier, that gives you the reward. So we have a lower bound that we can work with. And in practice, you might not want this lower bound because you have to train a classifier. You can even get a even looser lower bound that doesn't have a classifier. So compared to the previous formulation, you actually just drop the denominator here. And because P of S given G is proportional to E to the R, we can actually just substitute R of S given G for log P of S given G, right? And because R is something that's contained in your offline data set, you can actually use it as it is. And what's interesting is that we actually get a tighter lower bound to the original KL divergence by not using the reward that's given to you, but rather using this reward to train a state classifier. And what's the intuition about this, right? Basically, you actually do better by not using the reward given to you. So the way I think about this is that this ratio is actually an optimistic reward, right? Because you don't just want to maximize the reward that's given to you, but you want to actually encourage the policy to visit states that's like actually underrepresented in the offline data set, right? Because if DO is low, then this ratio is higher, right? So that's like a notion of optimism. But again, if you blindly optimize this, then you might learn a policy that's too optimistic and just doesn't learn a coherent policy at all. So in addition, you want to incorporate this regularization term to make sure you're not too far away from the offline data set. So it's like a really nice combination of optimism and pessimism. And we'll show that this actually gets you better performance than just optimizing this. But obviously the downside is that you have to train a classifier to learn this. Whereas here, you just use the reward that's given in the offline data set. Yeah, but the problem with any of these super nice lower bounds is that the expectation of the first term still depends on your policies rollout. So you still can't optimize this in the offline case. And here is where like the notion of state occupancy matching comes in, right? So we take the objective that we wrote down, the lower bound in the previous slide, where we use capital case R to denote, the reward function you use in either case, whether or not you use a discriminator or not. And then we actually just rewrite the optimization problem from an optimization problem over pi to optimization over the state occupancy distribution. And to make sure the occupancy distribution optimized is actually valid, we need to add this constraint that we have, the Bellman flow constraint, to make sure it's a valid one, right? And here I suggestively wrote a P here to denote the primal problem. So you see where this is going. The primal problem is typically, in a lot of cases, hard to optimize. And what you do is by using ideas from duality, convex duality, and in this case, it's something called Fenchel duality. The technical definition is not super important, and it's in the paper. But basically, if you use duality, you can actually get the dual problem of this primal problem. And the difference in the dual problem is that if you look at the expectations in this dual problem, it's entirely something that you can sample from the offline data, right? Because this expectation is, first of all, over the offline data set. And then the initial state distribution, the goal distribution, is also something that's in the offline data set, because the offline data sets contain trajectories, right? So if you want to sample from an initial state distribution, you can just sample from the first state in all the trajectories in the offline data set, right? So the dual problem gives you something that's not dependent on the rolling out your current policy at all, and it's only dependent on your offline data set. And you can see that it kind of looks like an objective over a value function. So this value function is actually originally the Lagrangian vector when you try to transform this into like a unconstrained optimization problem. But you see that it actually plays a role of a value function. And intuitively it says we want to minimize this one-step Bellman error under the conjugate function of f. And in addition, you want to make sure the value of the initial state is as low as possible. So you can think of this as sort of like natural pessimism. You want to push down the value of the initial state. So whenever you roll out from initial state, your value can be like delusionally high, right? So it has all the nice components of offline RL that you see in practice in this one objective. So yeah, feel free to stop me or ask me any question if any of this was confusing. And if not, let's continue. Let me just check up on time a bit. So given this dual objective, what we do is first just optimize this, right? Because here you can just estimate the expectation with samples and do stochastic gradient descent. And let's denote the converged V as V star, okay? And once you have V star, we just use it to compute this advantage term. So actually this one-step Bellman error is also like an advantage term in the RL speak. And you just use it to weigh a regression loss with respect to your offline data. Okay. And here this thing denotes the derivative of the conjugate function of your f. Again, what a conjugate function is not super important if you're not familiar with. It's just like an alternative way to write the original, let's say, KL divergence or other divergence you choose. And that's it. This is the objective we optimize. So far, I haven't explained anything about why we do this, why this makes sense, but I wanted to give you a high level of like what this algorithm actually does. And so the overall algorithm is quite simple. You just take the offline data set and you first just compute the dual value function, right? This is the objective in the previous slide. And then you just compute the policy using this objective. And then once you get your policy, you just roll it out in the environment. That's your policy that you're going to work with. And immediately we see something nice here, which is that the value and the policy networks are optimized disjointly. Like we don't go to step 2 unless we have finished step 1. So you can think, this kind of thing will have much more stable optimization practice than something that goes back and forth between value and policy network. But what's more important is that this objective actually has very, very nice properties, which we'll talk about right now. So actually, what's really nice about using this duality idea to not solve the primal problem, which is over the state occupancy distribution, but rather the dual, which is over P, is that once you get the dual optimal V star, you can actually directly get the primal optimal D star without doing any more learning or any more optimization. You just, for any state in action, you just figure out what the state occupancy distribution in the offline data set is, and just plug this in to back out D star. This might all seem magical and cryptic, but where it comes from is this very nice idea in complex optimization, where you can solve the primal problem with the dual. So this is Stephen Boyd's complex optimization book. It has a very nice chapter on this. You can learn more about it there. But now let's go back to the policy objective that we proposed here, right? What's really nice is that using this relationship, you know that this F prime star thing of the advantage, the F advantage, is precisely the ratio of the D star over DO, right? And now because you're doing policy regression using your entire offline data set, which is DO here, you see that the DO and the DO here will cancel out, right? So you're just left with D star in the expectation like this, right? But what is D star, right? D star is the occupancy distribution corresponding to the optimal goal condition policy of the original problem, the primal problem we posed. So in short, by doing this F advantage regression, GoFAR is actually just giving you doing behavior cloning with respect to the optimal goal condition policy. And this is very nice because in a way, behavior cloning with respect to the optimal goal condition policy is the best that you can do without any additional assumption. And it just gives you this property for free because we did all the convex optimization stuff correctly. But this is very nice, but what is the relationship between this objective with all the stuff that we have seen before, which would use hindsight experience replay to generate artificial data for policy learning, right? Which is quite standard in online reinforcement learning. And what we'll show is that our objective actually does what I call the implicit optimal hindsight relabeling. So what does this mean? Like, what do I mean by implicit? What I mean is that we actually do hindsight relabeling in the optimal way without actually doing it. So how does that work? So let's dive into it. So recall that this was the original objective, F-advantage regression we had, right? If you just do Bayes' rule, you can write out this double expectation in the opposite direction. Instead of first sampling a goal and then figuring out the distribution of state and action that that has appeared together with the goal in the offline data set, you can just first marginally sample state and action from your offline data set, and then figure out which goals actually appear together with SMA, right? This is identical way of writing it. And then I'm going to absorb this advantage term into this distribution over goal, right? So the way to think about P tilde, it's some sort of goal relabeling distribution, meaning that let's sample a state and action from the offline data set. And then this is the distribution that you use to sample to label a goal for this particular state action pair, right? So we know that P tilde of G given SMA can be thought of as some goal relabeling distribution. But the critical question is like, which one is it actually? So just to make this concrete, we can actually use this formalism to write out another relabeling distribution that's commonly used in practice. So this is hindsight experience replay. Giving a trajectory, the distribution, the relabeling distribution that her uses is just some categorical distribution over future states, right? Right. So I'm just mathematically writing down what her is in this notation. But that's not what P tilde does. P tilde doesn't label a state action based on some categorical distribution over the future states it visits. What it does is something more interesting, which is first, okay, this is just the previous slide, right? The P tilde thing, right? But we also know that the policy that GoFAR learns is minimizing this, which is, the behavior cloning with respect to the optimal policy, right? And because these are just equivalent way of writing the same objective twice, the distribution that's in these expectations must equal to each other, right? So this equality must hold. And we don't actually have to explicitly write out what P tilde is. It is just the relabeling distribution such that this equality holds, and it is implicitly defined as such. And given this equality, it's clear that GoFAR actually will make P tilde the optimal hindsight relabeling distribution. So after you relabel everything using P tilde and do behavioral cloning, we're actually simulating learning from the optimal goal condition policy, right? So that's what I mean by it does the optimal goal relabeling. And the best part is we never actually have to do this P tilde G of X given A, compute it, we're using it to relabel explicitly. It's actually just implicit in our objective. Like by doing GoFAR correctly, you actually just get simulation of this like relabeling mechanism for free without actually having to do it at all. So in practice, whereas other method, you have to implement hindsight experience replay. For ours, you don't actually have to implement it. You just have to compute the value function correctly and then do policy learning. And finally, a very nice theoretical property is because we are doing behavioral cloning with respect to the optimal policy. Behavioral cloning is just supervised learning, right? And we understand a lot about getting a theoretical guarantee for supervised learning regression, right? So basically, the theory says, as long as the offline data set has coverage over the goal distribution, where the optimal policy state action distribution conditional goal. So basically, the offline data set contains the state action that the optimal policy would visit conditional goal, then we get this kind of like guarantee on the value function we learn with respect to the value of the optimal policy that scales with the size of the offline data set. So basically, it says in practice, the bigger and more diverse your offline data set is, the better. And this is very interesting because typically, if you want to get a bound on behavior cloning's performance, you need the size of the expert data set to grow big in order to get good performance. But in here, we don't need the expert data set, but just the offline data set, as long as this condition is met. So this is like the theoretical basis for why GoFAR can be very scalable in practice, because you just need your data set to be more diverse and bigger, and then your performance will monotonically get better. And this kind of strong guarantee is missing for prior work. We don't understand when they work and what kind of data set the prior works require in order to learn like an optimal policy. So this is another distinction. So overall, what have we done? We have reduced goal condition RL to state matching. And then we derived an imitation learning objective from this state matching perspective. And in practice, it's very simple. You just train the discriminator, which is optional, and then you train the dual value function, which is actually a convex objective in the tabular case. So really easy to optimize. And then you just take the dual solution V star and do this advantage regression. No need for any hyperparameter related to hindsight experience replay. And we also see that it does a lot better because we don't need to tune this hyperparameter. So here's the full algorithm, which I won't go into. And let's just jump into the experiments, okay? So in the simulated setting, we assume that for each environment, we have a mixed data set of 10% expert and a 90% random. We needed this expert data set just to make sure, you know, the assumption of the theoretical result is kind of met. Basically, you need some good data in offline data set, right? Otherwise, no algorithm can learn a near optimal policy. But in the case that random data set is actually sufficient to cover the goal distribution, we actually only use the random data set. And that is the case in the simulated, you know, valve turning task and this region task. But for the middle 4 tasks, random data set is not enough to cover the expert distribution. So we just additionally give it a very small amount. And also the reward in these environments is sparse reward. But since we train a discriminator, we can do better than this. Okay. So we compare to a lot of the state-of-the-art algorithms, such as goal condition supervised learning, weighted goal condition supervised learning, then also DDPG with hindsight experience replay. And this method that's coming out of Google called actionable model. So for all the baselines, we actually tune the hindsight experience replay ratio, right? We tune the best number from 0.2 to 1 for the baseline. Whereas for ours, you know, we don't need it, so we actually don't have to do that at all. So actually, I'm doing the baselines a favor by giving them more, you know, hyperparameter tuning than ours. So the first metric we consider is success rate. So basically, which method gets close to the goal most often, right? So these are the percentage, or 40%, 26%. So you see that on this metric, our method is already the best one compared to all prior work. And on 2 tasks, pushing task and turning valve task, our improvement is actually statistically significant over 10 random seeds. Okay, so this is already a sizable improvement. But success rate is not the only metric that really matters, right? Because here, success rate is defined as getting within an epsilon ball of the goal, right? But it wouldn't distinguish a method that always just getting right inside the epsilon ball, where actually gets really, really close to the goal all the time, right? Because under success rate, these 2 methods are equivalent. So another metric we look at is the final distance to the goal. So which method gets actually closest to the goal? So these are like the Euclidean distance in the goal space. So on this metric, we again, is the method that gets to the goal the closest. And the reason why we do so much better here as well is because instead of the sparse reward, we use like the discriminator reward that offers us like a sharper reward to use for policy optimization that actually encourages reaching the goal like as close as possible. All right. And finally, we also present this discounted return table, which is the sum of the cumulative reward over the ROIAL. So basically, this method would reward an algorithm for getting to the goal as fast as possible, because once you reach the goal, you're going to stay there. This is going to accrue more reward over the course of, you know, a policy ROIAL, and also most precise, because the closer you get to the goal, the higher reward you get. So on this final combined metric, we again show that our method is the best out of all these quite competitive baselines that came out over the last year. And you see that for the supervised learning methods, that learn a policy by regression, they kind of require hindsight experience replay to be turned on at all times. If you make these any number that's not 1.0, they actually collapse in performance, as we'll show. For actor critic, the numbers are less, but you see that you needed different per rate for the method to work well for different tasks, right? But obviously in offline setting, you can really tune the hyperparameter. So by getting away with it, it's actually GoFAR is a much easier method to work with. Right, so now let's do some ablation study. We figured out theoretically GoFAR doesn't need hindsight relabeling. So let's actually just do an ablation for GoFAR and baselines with and without hindsight relabeling, okay? So the original GoFAR doesn't use hindsight relabeling, but what happens if we actually add her to GoFAR? What we see is that adding her doesn't actually impact GoFAR's performance at all because it's already learning the policy from the optimal policies distribution. So it doesn't need relabeling to provide you the extra mileage that gives you better training signal. But in contrast, these dashed lines are the baselines aggregated performance on all of the tasks with hindsight experience replay. But if you take experience replay out, their performance will drastically decline, showing that because other methods are largely inheriting artifacts from online Go condition RL, if you remove those artifacts, they're not really tailored for the offline setting, and they don't work quite well. And when we remove it, we're at it, doesn't matter. And finally, we have a baseline or ablation that doesn't use the discriminator, but just uses the binary sparse reward as given. As you see, it kind of does worse than the one with discriminator, but it's still far superior to all the baselines, showing that if you wanted a simpler version of ours, use the binary one. That's still better than the baselines without any her. But if you want to optimize for performance, let's just train an additional discriminator. Okay? And I think one additional property that's really nice when your algorithm doesn't depend on hindsight experience replay is that it's more robust to noise, right? So let's say this is your offline data set, right? So because of noise in the environment, you might have reached a goal by accident, right? So if you use this goal to relabel your trajectories, then this goal might not have been able to, you might not actually be able to reach this goal again if you just weld the same action in the environment, right? So this is what I call the false positive phenomenon for hindsight experience labeling when noise is present. You might have reached goal due to noise. And so when we test on one environment where we just add more noise into the offline data set, so basically the offline data set is now collected in the environment with noise added, we see that whereas our method declined gracefully with more noise added, the baseline's performance degrade much more severely or significantly compared to ours, right? In particular, the best performing method initially without noise, which is actionable method or actionable model, will suddenly collapse to zero when you add sufficient noise, meaning that these methods suffer quite a bit from this false positive phenomenon. And because our method doesn't do relabeling, it doesn't suffer from this phenomenon, and it's much more robust to environment noise. So these all sound great in simulation, and we actually show that our theory holds up to practice in a real robot experiment. So we consider this 9 degree of freedom tri-finger setup that needs to rotate a valve to a certain configuration. So in our evaluation, so in our training, we wanted to reach any configuration, but in our evaluation, in the videos, the initial position is here, and then we always just want to evaluate rotating 90 degrees to this like white line here. And so the data collection here is actually just by motor babbling. So basically just randomly like move the robot to collect data. And what we figured is that on this task, just by rotating or moving the robot randomly is actually sufficient to move the valve to different configurations, right? And our theory says as long as the data set covers the goal distribution, it doesn't matter how it is collected. So here we actually consider the most adversarial setting where the data set is just collected by random policy. So here's like a really sped up version of the data collection, but it's random, but you'll see like the valve is like turning into different configuration just because, yeah, randomness is good enough. So using this data set, we again compare our method to all the baselines, right? So this is quite adversarial because in the real world, first of all, the data set we give is pretty bad. Second of all, because of real hardware's wear and tear and actuation error, there's like inherent noise in the environment, right? But because we said our method is able to handle noise and has a theoretical guarantee even when the data is random, we indeed do see that our method learns a much better policy than the baseline, which mostly learn like a random policy that doesn't really do anything, showing that when you get the theory right in simulation, you can actually scale to like practical applications such as dexterous manipulation. And let's look at some video, right? So here's like 3 different deployment of our policy. You see that it's able to rotate to the right place. And in the third run, when you initially overshot, right? You see this initially goes over the line, then would actually be able to rotate it back to the correct position, showing a pretty robust policy. And then here are the baseline. The baseline, except AM, doesn't really move the robot at all, showing that with random data, it's actually quite difficult. And they don't scale to real-world deployment. And here is just like more like static picture where you can see how our policy rotates the valve to the correct configuration, whereas the baseline doesn't do anything. Even though these baseline were able to learn something in simulation, deploying the same algorithm just failed in the real world, whereas ours just kind of succeeded out of box. Okay, so do we have time? Maybe I should just stop here and skip the last part. It's not super important. You can see the paper for more detail, but let me just summarize the method again, right? Instead of borrowing or just adapting online Go conditional RL method to offline setting, we derive a method from the first principle of safe matching, which has this really nice teleportation intuition. And we show that the algorithm is stable because we don't interleave policy and value network training. It doesn't need hindsight experience replay. It has performance guarantee. And the last part I didn't talk about, it has planning capability. And it has quite strong results in both simulation and a real robot. So I really think you can extend this to like much more complicated environment and the task, and can serve as the bedrock algorithm for learning a generally capable robot that can reach all kinds of configurations in your environment. And thank you for listening. See the project website for the paper, the code, and a lot of more animations. And now let's get into Q&A, and I'll take questions and discussion.